Alright everyone, welcome to a review for the mobile test stand by Florida Tech Rocketry for Florida Tech and Larson Motorsports. Essentially this is going to be a overview of the structural aspects of the motor test stand itself. That's because we're still kind of tracking down some of the information done for the control systems for the test stand, and we're still kind of tracking that down from the previous avionics league. So this kind of review will mainly be covering everything related to the trailer, the thrust structure, the kind of design of the overall test stand, and how everything, or kind of imagine everything will work. And that's basically going to be all based off certain like requirements and criteria that we previously discussed in a meeting. And I guess that's kind of like the next thing to get right into. So these are kind of the notes that I took when we had that meeting with Dr. Wild and Dr. Kish. Essentially, it kind of helped us explain some of the requirements for the test stand. The notes are over here on the right, but the kind of simplified bullet points are on the left. Essentially, we need to build a mobile rocket test stand. It needs to be able to be driven around. It needs to move from Florida Tech to anywhere from just down the road at a local high school to all the way across the country for a national rocketry competition or something along those lines. Essentially, we want this thing to be road legal, protected, and be able to travel long distances without fear of it getting hurt or having to completely rebuild the test stand upon location. We want to be able to get there and kind of just easily assemble it and kind of set it up and as quickly as possible with the minor amount of tweaks. It's okay if we do certain amounts of tweaks and preparations before we drive out to certain locations to kind of speed up the process, but essentially we want it to be as simple as possible to kind of set up. And going off that simple operation, we also want we want it as safe as possible. So including things like remote starting and stopping capabilities, as well as viewing capabilities, so then we can make sure to see the test stand at all points and see some of the critical areas such as the tanks and valves and the load cell area, to make sure that there's nothing going wrong, and if we do witness something, then we can stop the test at any point. We will also be I'm not too sure, but I'm assuming we will be designing certain fail-safes into the controlling hardware for the controlling software for the test stand itself. So then, if there are certain pressure spikes or temperature spikes or anything like that that we're not expecting, the system will shut down and purge. But that's something we're gonna have to talk more about once we kind of dive into the electronics and the software side of things later on. Also, going off safe operation, we're probably going to want to have some kind of remote fire suppression or something like that can help reduce potential damage that could happen from fires getting out of hand or anything like that. Another thing that we want this test stand to do is we want it to be very education focused. We want pretty much lots of sensors with pressures, temperature, force, etc., pretty much all that kind of stuff. We want everything clearly labeled and easily accessed, and we want kind of cameras to be able to help view everything for teaching purposes later on, so then you can also maybe potentially teach online courses or kind of help supplemental learning for labs. And a kind of good analogy to this would be the jet turbine lab, where there's kind of like where at least where I think where we were thinking was this kind of like that jet turbine lab, where there's various pressure, temperature sensors and fuel fuel flow sensors as well. And essentially, we're thinking is with all those sensors, then we could potentially ask students different questions for different labs. So then we could give certain measurements of say pressure or temperature at different areas in the motor and ask them to calculate the theoretical, say, value, and then we could actually have a physical sensor there too to kind of compare their results to. So that might be a really good way to kind of help students learn about these, like the realistic losses in these kind of systems. We already talked about ease of assembly and setup. Another big thing that we did mention is that, or I just haven't mentioned yet, is that we need this test stand to be size adaptable. We don't really know what kind of motors we're going to be putting on this. but we do know that we would really like to be able to cater to liquid, hybrids, and solid motors, ranging in ranging in size, overall length, as well as diameter, and as well as ranging in thrust. I don't think we got a clear um, value for a target thrust, but we kind of assumed that a decent size kind of wow factor engine would probably be around 500 pound force, and that would be kind of like the max expected. And we decided to kind of throw a minimum safety factor of 4 on there. So essentially, we'll be designing for a thrust structure of right around 2,000 pound force. Um, but the kind of typical range I guess we're expecting or would be right around 100 to 300 pound force, and then the max expected we're thinking is right around 500 pound force. But since designing for 2000, we'll kind of have a lot of wiggle room, especially on the lower end of the thrust range, which will be real nice. Um, I guess that's kind of it for the majority of the test stand requirements. Oh, well, yeah, we'll kind of go through the rest of those requirements as we go through the design. Um, this is just some initial sketches, initial ideas, but pretty much this is kind of the main thing that we're thinking right now. This is just what I'm calling it in the CAD software, just to kind of make it easy for me to remember and kind of work off of, because I can make a naming convention off this. But essentially, it just stands for Florida Tech Rocketry 2,000 pound force thrust mobile test stand. And it's kind of comprised of these major components. One would be the trailer, and that's being kind of worked on and provided by Larson Motorsports right now. And this actually includes their newest CAD model. So we'll kind of show you where the supports that they added and how we can kind of integrate, say, adding the frame or the thrust structure and tying it directly into the supports that they made to kind of have the strongest overall connection between the two. But essentially, so the first part was kind of the trailer where everything is sitting on. You can kind of see it here on the bottom. It has a red plate. The colors right now are pretty much just to make it look nice. It's not. We still kind of have to figure out colors and say logo placements and all that. But this was just kind of done to get you kind of a visual aspect of it. But essentially, we got the thrust takeout assembly right here. So this is the kind of the major thing that will allow that will withstand the thrust. Can change for various motors lengths and diameters, and we'll have like sensors placed on the inside somewhere, but we'll have to talk more about exactly what kind of sensors and where we're going to place them. But essentially, it's kind of this self-contained unit that can be fabricated on its own and then placed on the frame or the trailer itself and then bolted into place, or it can be removed and used off of the trailer, and then that allows us to be able to actually remove this thrust structure later on if we want to build, say, a bigger thrust class engine and want to test it. We could totally remove this part and then attach another bigger thrust structure to it, or at least one that's configured differently that can work for different types of engines than what was initially kind of considered. The next is kind of like this tank frame back here. So that's kind of like this big box with these doors. So essentially, this black part on top is actually the roof. So this is where there would be like a canopy over it. Right now, how it's currently made is that this canopy can be raised or lowered. So when transporting, it would be lowered, the walls would be up, everything would be secured together, and there would be a canopy over everything. So it'd be kind of protected from most elements. But then when we're actually going to go ahead and use it, we just roll up the tarps or roll up the canopy, pop up the ceiling, because these K-bottles are only about 5 feet tall or a little bit more than that. So the clearance wouldn't be great, so we probably should add some kind of taller ceiling, but you wouldn't necessarily want to drive around with a taller structure than you have to, because then you just run into a lot of more problems. So that's kind of why I made that go up and down, so we can actually move this up and down to just create more room on the inside. The doors right now, this is kind of a new addition, but we were kind of thinking that if we wanted to have, say, K-bottles or tanks permanently, or not permanently, but mounted inside the trailer as opposed to the side like we originally had, we would probably want to have some kind of ramp or something to be able to walk up on and change these K-bottles out easily. So that was kind of the idea behind having these doors that can also act as ramps Um, I'm not sure if exactly that's something we want. It's just kind of something I thought might be nice. We could definitely get away with not having the walls, or not having these kind of foldable ramps that act as walls as well. But we can kind of discuss that, and if there's a glaring, I don't want to say issue or problem with that, but or if we don't think it's necessary, just let me know, and we'll sit down and have a conversation about it, as well as anything else throughout this presentation. If you don't think, or if something doesn't sound or seem right, just take a note of it, and we'll get back and we'll kind of talk about everything. But essentially, that's kind of the idea of the ramp walls, so you can actually either wheel stuff up and down or make it easier to carry stuff up and down. We could as easily as well just have a K-bottle dolly that also lifts, and then you just use that. That could be also another really easy way. So depends which way we kind of want to go. But essentially, in this frame, this kind of holds the thrust. This is kind of like the big thrust plate. So I mean, not thrust plate, blast shield. For the tanks and the majority of the piping, because the majority of the piping is going to be back here in this center area of the frame, and it's going to kind of come out this little hole and into the engine itself. And we're thinking of having some kind of port system here, where essentially you have preset ports that have preset channels to K-bottles that are filled with whatever we decide. And essentially each port, for whatever you need for a test, you just connect it up to that port, and then you're kind of good to go. At least that's an initial idea. But essentially that kind of big blast wall here would kind of serve as our logo wall too, so we could kind of like sell or help promote our FTR sponsors or Florida Tech sponsors, or as well as Larson. Anything like that, we can just throw them on this kind of front area. We can definitely make it look a lot nicer. This is just kind of like my initial, just throw it on there. Other than that, piping, there's no piping in right now. That's actually going to be one of the things I'm going to be working on soon, is just kind of creating preliminary pass and getting that over to Fluids so they can run some GFSSP on it and let us know what's if it looks good or not. And then after that, so those are the kind of the two major structures. The next one after that is just kind of supporting equipment. So this includes anything like, say, these jack stands to help push the trailer off of its wheel, cable straps to kind of help secure the whole thing in place while we're firing it. Because while we're firing this, we're probably going to want to have cable straps in the corners over here, either bolted and then probably onto the thrust structure itself. I add little eye bolts. You'll be able to see it later, but essentially you can just mount to it right here, strap it into place, so then the thrust is kind of contained directly in the thrust structure itself. But anything else like anchors or, say, cameras, this would be where all the cameras equipment and all the pressure sensors and all that kind of stuff gets thrown into. But we still got to characterize that out fully. But for now, since we're kind of aiming to more have, like, say, a solid ready structure system for spring, we kind of just care about really the supporting, the thrust takeout, and getting the frame ready, so then we can start to put the piping and the bottles in when we're ready. But as far as that's kind of the rough overview, this kind of shows you how big the whole thing is. So at its longest point, when it's kind of retracted with no motor in, we're going to get right around 120 inches. So all these are in inches. We're going to get height of around 86 inches, width of 52. And then these are kind of like specific for the frame. The frame is 56 inches deep, and then it's when the walls are folded down, it's almost 150 inches. So it does take up a decent amount of floor space, but it's fine because we're not going to be wanting to put it next to anything really when it's firing. And then when it's stored up, it should take up the regular floor spaces with trailer just a little bit higher. So we'll just need to make sure to have a ceiling or a roof whenever we're storing it indoors that it's tall enough. This is just kind of a wraparound of the trailer itself. So this is just kind of like just to show you how it looks 3D. So you can actually see how it looks with the walls folded up. And I'm going to go ahead and try to attempt to move the wall down, but in CAD it's kind of annoying. But you can kind of see how the walls fold up or fold down, and then from there people can walk up and down that ramp, as well as kind of move equipment up and down pretty easily. That was kind of like a quick zoom up on the thrust structure, but this is kind of showing you how the tanks and the frame is. The piping would go inside there, come out right around here, and go right into the motor. So this is the thrust structure. So this is what I mean by having an extending stabilizing ring. So essentially this thing will move forward and contract backwards and pinch in and pinch out to kind of account for various motors. And then it has a linear guide that goes into a load cell. Essentially, we'll have to make adapters for each motor, but as long as you make the adapter to a certain standard, it'll always fit into that linear rod, and then boom, we got pretty much as close as axial thrust measurement as we can get. And that's just showing you the other side, how it looks when it's fully down. All right, moving on. These are just kind of some pictures to help, I guess, again, picture it. Walls up, walls down. This is just kind of a hidden view, so hidden walls, so you can kind of see through, and you can actually see the frame supplied by Larson with the supports kind of put in, and you can see these two linear areas, so we can actually bolt directly into the thrust structure, but you'll kind of see that in a second. Here, this is just a top view. Just again, help probably for these bottles we can space these out however we want. We're probably gonna have a floor in here. I just didn't add it, but we're probably gonna have a floor that the K bottles are gonna sit on, and just to make it easier and cleaner. K bottles, we can, right now there's just 4, but I think I was talking to Propulsion, we're planning on having 3 on each side. So we'll have a decent amount of propellants and different choices, so that'll be nice. But the piping will mainly live in this channel right here, with some probably going around out the back side or venting upwards. We'll kind of talk more about with that with Propulsion before we kind of finalize. But piping is still a decent way off. This is just a top view, but with the floor hidden, so then you can actually see the supports. So these are the supports that Larson added. So there's this one main strut in the middle that we can actually bolt to for the thrust structure. So we can actually do 2 bolts in various locations along the middle. But as you can see, it doesn't really line up on these supplementary kind of beams that they added. So we might be able to add, like, say, just a bar that goes, like a U-bar or something that goes across the whole thing and bolts into place. But we'll see. Otherwise, we can just bolt directly into the metal plate in the flooring. It won't be as strong in those locations, but I feel as long as we have a majority or have a decent amount that's bolted into the main beam itself, and then some in the plate, it should be fine. I guess I'll have to run analysis on that to make sure, but I have a feeling it should be fine. And then the frame itself, we can actually bolt. So this is the I-beam on the sides. We can actually bolt directly onto the outside of the I-beam. So when actually you can drill through that I-beam and just put like a 1/2 inch or a 3/8 inch bolt through, bolt it into place, and it should be great, or not great, but should be strong enough. And we'll have to determine the amount that we'll have to put on the sides here and here, and then we'll just bolt where we can on extra supports down in the middle. So this is just kind of some visualizations of the tie down idea, like how we're planning on trying to die it down. These are some old graphics, so they're not exactly as accurate as what I just showed you, but essentially we want to have tie downs somewhere at an angle. We have a lot more research on this for tie down stuff. I didn't really spend a lot of time on this, but I know other teammates have. There's a whole grading and angles and pretensions and all that kind of stuff. So we'll be looking into that to double check for the tie down stuff. But depending on where we are and whether or not we have access to bolting into concrete or say asphalt, or if we're gonna have to rent, like, say, jersey barriers or something, then we might have to do that to kind of ensure that the trailer's not going to go anywhere when we're actually firing. And then so that's kind of like the straps idea. We might have one on the other side too to kind of counteract, but this is kind of like the main idea, is that thrust pushes you this way, these kind of pull you back. Pretty simple. This one on the right is kind of like the camera placements. So this is just my initial thoughts. We probably want to have one kind of looking over the whole system, and then we would probably want to have one on the inside on each side as well, just to kind of view the bottles and make sure and check, say, like important connections, just to make sure that we don't see any leaks. And then down here, there's just I put two cameras, one to kind of be at the exhaust end, so you can see the kind of like normal to the plane over here. You can see the diagrams right there. But essentially, and then the other one would be kind of looking in at the load cell. It would be zoomed in at the load cell area, or not the load cell area, the injector area. So then if and when we do, or whatever, when we do one, we'll be able to tell if there's leaks, or if just something goes wrong on the injector end. We'll be able to see it, and we'll have footage of it. So then if we need to go back and kind of review, we'll have the footage for it. That was kind of the idea behind that. But camera placements and cameras, we can always talk about where we want them and where we think it'll be the best. But after this, this is kind of dive into the thrust takeout assembly. So these are kind of some pictures of it. You also have some cutaways to help you kind of identify. But essentially, it was designed to be 2,000 pound force, size adaptable between 3 inches and 8 inches, and it actually can go lower than that. And then if you make a certain adapter, you could probably go a little bit greater than 8 inches and go maybe up to, I think, 9 inches in diameter. But then at that point, if you're going to be doing something out of this range, you would probably need to either make a specific, so if you're smaller than the range, then you'll just need to make a specific adapter to fit into this and take advantage of the linear system. Or if it's way bigger, say in diameter, then we'll probably need to go ahead and make a specific kind of thrust system for that specific motor. But essentially, it's mainly made out of 2x2 galvanized steel framing. Essentially, they all come pre-punched, so they all have holes for mounting. And essentially, the idea is so then we can move this thing in and out and kind of lock it into place through locking pins. And then it also allows us to bolt into place where we want it to, as well as add little kind of fittings for, say, sensor mounts or camera mounts or anything else like that. But essentially, it's made by 2x2 framing in the back end, 1.75 inch framing on the front end, so they slide into each other essentially. Carbon steel plates were these two guys. This is a slightly old graphic, so this thrust plate doesn't look the same anymore, but it essentially serves the same purpose. But essentially, there's one steel plate that's thinner, 1/8 inch, that serves for a bolting location for a linear guide. Linear guide is roller bearing right here. Most of these parts are all coming from McMaster, so we can buy it in bulk and get a discount. So that'll be pretty nice. But essentially, that thin plate holds the linear bearing, and then the linear bearing guides the kind of motor adapter. That's what this kind of collar looking thing is, into the load cell, and then that's where the load cell is mounted on a thicker back plate. Right now, I've spec'd out a 2,500 pound force load cell. When we initially looked into these, there's a whole bunch of different manufacturers, and they have a whole bunch of different like plug-and-play systems. So we should be able to buy one and be able to add more load cells and sensors to them, and they should all be able to work together. I'll have to double check, but at least that's what I saw from some research into it myself. Again, we'll have to spec all that out and choose it. But for the most part, it seemed that the load cells up to a certain force, their pricing didn't change. So, and the accuracy doesn't change really. It's just kind of designed for a maximum. So if we go with a 2,500 pound force load cell, it'll pretty much give us the same accuracy, and it'll be for the same cost as, say, for 1,000 pound force or even a 500 pound force load cell. So it might be better just to go for a bigger one, but again, we'll kind of have to choose and spec them out specifically. We got threaded rods, and then we got the roller bearing, like I said. And then if you these kind of clear panels here you see around here, these are kind of like, I was thinking primary acrylic blast shields, kind of like, Mythbuster style, just so then we can see through this, and it'll add an extra barrier for our cameras. So essentially, if we have cameras here, you'll be able to see in this area without risking, well, I can't say that with any certainty, but if there is a slight, like, say, gas pressurization or something goes wrong in this area, these kind of shields will help protect shooting things up or radially around. If it happens at the nozzle end, then it's kind of already over here in the middle of the way away from, I don't want to say way away, but it's farther away from everything. So it shouldn't be as much of a risk to the cameras or anything like that we would want to have. And then after that, okay, yeah, so then this is just kind of like a graphic showing what I was talking about. Solid motor case, acrylic black shield, motor adapter, linear bearing, thrust plate, and then this is kind of like the same, the motor adapter. This is kind of like that rod. So imagine a cone with like a half-inch steel rod on it, and that just slides through the bearing. This is kind of a full cutaway where you can kind of see this is the extended area. These are the kind of stabilizing. So this is the main thrust. This is kind of like the stabilizing attachment. This could be fully removed and a plate can be added to the front instead if we were going to do, like, say, a really small motor or a specialty motor or something like that, and we needed to do something fancy on the back. You can completely remove this gray front piece and add a specific mount if we need to in the front. This is okay, so then this kind of shows you a nice little configuration change. So you can kind of see the difference between it being, say, well, actually this kind of shows you the difference. What I was talking about is, like, so it can either be extended to, say, this is just showing you with a 6-inch outer diameter 4-foot motor that the whole thrust structure can kind of be extended to stabilize it, or it can be kind of collapsed for smaller motors. So this is kind of what I was imagining as, like, say, a solid or a hybrid motor, and this would be kind of like a liquid, smaller or not as long but fatter in diameter kind of motor would be like the liquid, and this one would be the kind of solid. It can go much smaller than this. These are just kind of two potential sizes that we could use, and I just wanted to kind of demonstrate how it would move in and out. But essentially this shows you we have eye bolts here that we can actually use to strap to. If you're wondering what the holes in the plates were for, that's for if we have piping needed. So then if we are doing a liquid, we will have to have, say, lines that go down here, or even flex lines that go around, and then we'll have to manufacture, say, this motor adapter for the liquids would have to be some kind of like bird cage structure, or what is it called, injector cage, I think, injector cage structure, where there's like it's a space on the inside that we could allow for mounting of the piping directly into it. But again, we can mess around with that, and that should be a pretty easy thing to work around. Yeah, and then this just shows you how the stabilizing thing works. So essentially there are roller balls on the ends. So essentially when we get the motor, we slide it in this way, we mount the adapter to it, open these guys up a little bit, or at least open the top two, leave these guys where they should be, then we slide them into the structure and into the linear bearing here, and then it'll be in contact with the load cell, and then we just tighten everything to make sure that it's all lined up. I think we'll need to make some kind of I don't want to say guide, but some kind of template or something that can fit somewhere into this assembly to help ensure that this is the same, like these two, like, say, the circle of the motor casing is as concentric with the load cell as possible, because if this gets too far out of alignment, then it can cause a lot of funky loads down here and getting some weird readings. So we'll want to try and find some way to ensure that, whether that is just measuring this distance, measuring the um, diameter of the motor, and then just subtracting the two and having a little bar that you just measure down here. That could be a simple way of doing it, but we can brainstorm and find a cooler way. Okay, so that's the class version. So the next step, I guess, would be to kind of talk about the analysis. So I went through and analyzed the whole thing. So this was from a previous run, but I kept the graphics because they're kind of the same. It's the same thing. I ran a previous run with a plate that looked like this. Essentially, it was just a thinner plate with kind of stringers welded on to kind of add support, but that didn't really work out too well. So I went ahead and redid it and changed it. But essentially, this kind of shows you how I did it. So I applied 2,000 pound force to the load cell button, which is right here. And this is a button style load cell. We could always go with like an S style or a threaded, or say a threaded rod, but this one allows for it's just a simple contact load cell. So it can be used a variety of different ways, and we can make tons of different types of adapters for this kind of load cell. So I figured it might be the easiest. Plus, I've worked with these personally, so I kind of know how they work and how they mount. So that's kind of nice. But essentially, what I did is I applied the material properties. So the plain carbon steel to the two plates, and then the galvanized low carbon steel to the tubing itself. All of the contacts are considered welded. I didn't do any extended analysis into the welds, say for reduced yield stress at the joints. I can, but at the same time, I don't think that we're going to be running around 2,000 pound force, so I can definitely run it. I'll just need to take some time out to do it, of course. But you'll see the analysis. Yeah, so fixed geometry conditions. So essentially what I did is that I took places where we could bolt it into the middle I-beam, and you can kind of see those highlighted. But essentially, I think there's 2, 4, 6, 8, 10. So there's 20 bolts total, locking it into place. And these are all 3/8 inch, so these are all concentrically fixed. So on the inside, so imagine if there was a rigid bolt and it just kind of stuck in there, and we knew that the bolt was not going to fail. That's essentially the condition. Face condition, so it's laying on a surface so it can't warp down into it, but it can slide across it, so that's the surface condition. And then I also fixed the eye bolts in the front for where we could mount straps. Technically, there would be force applying the opposite way, but I figured it's probably just as accurate, or just, well, not accurate, but just as, not accurate, but something along those lines. It's just as, whatever. I fixed those to kind of emulate, say we have ratchet straps that get kind of bolted to those eye bolts, and then we pre-tension it to the point where it's kind of like the cables are really, really in tension, so it's like pulling the other way, but for now I kind of just fixed it in the analysis. So those are the fixed geometry. I don't know why I copied this twice. That's really dumb. Okay, mesh conditions. So I did 2 analysis. I did 1 on the whole thing, and you can probably imagine that my computer didn't like me very much. It took a while. It crashed a few times, but I really wanted to see how the thrust would translate through the entire structure. So I don't have those actually, no, I do have those pictures. I'm gonna pull those up. Sorry, but I think it's important to kind of see how it goes through. No. Okay, here. So I feel like this is a decent representation. So you can kind of see the thrust really doesn't leave the area. It doesn't leave the thrust plate too much, and you can actually see it better here. It really doesn't translate much past this plate, so that's good to know, and that's kind of why I didn't really see a need for, say, analyzing where the welds are going to be. But that was the old analysis. The new results are down here, but essentially these are just the material properties with the yield stress and ultimate tensile strength. And then these are just the material applications. Then this is the result. So this is the results of the new analysis. So based on the old one, seeing how everything was blue around the frame itself, essentially I took the plate out and I took the two pieces of the thrust structure it would be mounted to, and I fixed those conditions as if they were, say, quote unquote, well, they're fixed. It's a fixed condition. So essentially, if we knew that this point, this point, this point, and this point, we absolutely knew that and that's essentially where it's welded to the rest of the structure. We knew that that was not going to move and that was not going to deform. That's kind of what this is. This is kind of assumed to work off of. But then you can kind of see the results here. You can kind of see the front. We see there's a lot in between these circles, which is kind of expected. And if you're wondering what this kind of cylinder is right here, that's essentially what it's just to kind of help center the load cell into place and keep it into place. That's what I was thinking. And it also helps with the, it adds a little rigidity to it so it doesn't kind of deform as much. We don't need this, but essentially what I was thinking, this would be a 4-inch, it would be 1 inch high of 4-inch outer diameter steel tube. That's, I think, 1/16 inch thick or 1/4 inch thick or something like that. Cut and then just welded to the plate. We don't need that, and I can run the analysis without it, but I doubt it'll change much. But you can kind of see that the max stress is right around 125 MPa, which, if you remember our materials, way above that. So even our lowest one's around 203 MPa. We're running at like 90 less than that, or 75 less than that, so we're good with that. This is just a identification of where the max stresses are. So there's one up here in the punch tube itself, and then there's one in the bolt holes for where we attach the load cell. But as you can kind of see, they're small, they're kind of surface, and they're not very big, but this is where you could kind of expect cracks to form over a while, so we'll need to kind of keep an eye on that. That was that one. This is just kind of showing you how deep the stress goes into the material, and you can actually see like it looks hazy blue right in the middle. It's like that kind of shows you that the stress doesn't really carry through all the way the material. So that's, again, nice to know for the stress. Yeah, this is close up on the upper beam as well. And then you can kind of see way less. And that's our ultimate tensile. Now if we go to deformation, this is kind of our deformation of it. We're looking at a deformation. So this is if, again, 2,000 pound force is applied to it. And essentially it's where it's like 2,000 pound force is applied to the tip of the load cell, or the button of the load cell. But since the load cell is designed for 2,500 pound force, I'm assuming that it's designed to survive that, so it should be fine. So essentially I'm assuming that all of the force gets carried onto the contact surface behind it, so that's kind of why you don't see the load cell in these analysis. It's just to kind of remove the overall amount of elements that need to be created and features, so just made the analysis go a lot faster. And the result should still be pretty much the same. But then you can kind of see that causes a deformation of around 0.26 millimeters. So after numerous fires, that will probably be something that will need to either change the plates or do something to kind of mitigate that after many fires. But that's at 2,000 pound force. I'd have to run this at, like, say 500 pound force, and then just do like 100 repetitions and see how much, or like see if it survives, or see what kind of state the structure's in after that. So again, that's another thing to keep an eye on. But the way this is right now, it's just a simple 1/4 inch steel plate that just gets bolted in at the top and bottom, and then when we want to change it, you just slide it out. Unplug the load cell, and then just slide it out and change it out. And then this is kind of the frame stuff. This is just showing you where piping could potentially go. I'm not too certain exactly how that's going to look right now, but this is just kind of like basic. Hey, look, we're going to have the piping go to all the tanks, work around the system, and come out the bottom. Come out here. So I'll be making more detailed models of that soon, but I got to move and do a lot of other stuff, so that might have to wait a bit. And then I guess that's kind of... I need to do a little bit more on the frame and talking about it and trying to nail that down exactly, but this was mainly to focus on the thrust structure, because I know that's kind of like the first thing we want out. So speaking of that, we kind of want to... The next few things that we know need to be done is finalize the model, especially to finalize the thrust structure, so then we can start, say, making CAD drawings and parts list for that. So then we can start buying pieces and start actually putting stuff together. But this is where we're going to need approval, or at least communication and acceptance to a certain degree of the design from Kish and Wild before moving forward. I should have a basic BOM, and by basic I mean just, hey, these are the kind of like the total lengths of materials we'll need. This is kind of basic pricing for a steel plate for a certain dimensions that we'll cut our things from. So it won't be like 100%, it might be like 75% of what the final BOM might be, but it's essentially just to get a rough cost out, especially for specific parts. Just to kind of aid in the decision whether or not this is, like, say, a good thing to do or a good direction to move in. But I know we want to move forward quickly, so I'll try to get that done soon. But that should be either included with the email when this gets sent out along with the PowerPoint, or it will come soon after. But after that, so after creating the CAD drawings and parts list for as many parts as we think we need right away, which I think is mainly the thrust structure, and then potentially the frame if we can. And then we would want to create assembly manufacturing information, like how we're going to put this thing together, what's the best way to make this, what's the best way to attach it to the test stand. And then after that, pretty much go ahead and create initial piping layouts and test in GFSSP to make sure that we're getting the kind of fluid properties that we need for, say, our liquid and hybrid tests. And then and then we definitely need to figure out the controller side. I'm not quite sure who's working on that. I know we've kind of lost touch over break, so we'll have to kind of sit down and really nail that out. Colors, I really don't know. We can talk about that, and even just to a day, just have an in-person meeting and sit down and just be like, this color, this color, this color for this, blah, 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 all that. And then the branding and the logos stuff, that's pretty minor, but something we can just think about, especially if we know that people would be willing to give us money for, say, partnerships or brandings on the test stand itself. So that's something we can think about. But priorities are finalize the model and create the CAD drawings and parts list. But yeah, that's kind of it that's pretty much it for the thrust structure and the test stand itself. If you have any questions, again, just reach out. Reach out to me. My email would be included in the email. My phone number should be as well. Pretty much just let me know if you want to sit down and have a meeting with me. Otherwise, you can just send me an email with some concerns, considerations, or comments, and we'll kind of go from there. All right. I look forward to seeing you all in a bit. All right. Have a good holiday season, guys.